Good afternoon, everybody. Thank you for coming and joining us today. My name is Rowan Miller, and hopefully you're here because you want to learn about writing asynchronous ASP.NET applications. Async can be quite confusing at times, so during the next 75 minutes, I really hope I can take some of what I've gleaned from my own experience and from pestering people I work with at Microsoft and share it with you so that you can learn the same things in a lot less time. In our time today, we're going to take a very quick look through the history of async in the .NET framework. Then the bulk of our time together is going to be spent talking about the different scenarios where async can have an impact on your applications. And then at the end, I'm going to spend a little bit of time sharing some tips, some tricks, and some common pitfalls when doing asynchronous programming. So, history of async in .NET. In .NET 1.0, there was no asynchronous programming model. Feedback from customers was we needed it, so in .NET 1.1, we introduced APM, or the asynchronous programming model. In this programming model, I would start by calling a begin method, which would give me back a result. I would then need to write code to continually poll this result until I saw that it was completed, and then I could go ahead and call the corresponding end method, passing in the result, to get back the actual result to use in my application. This is complicated to work with, right? Nobody wants to write code that has to continually poll something to work out when it's completed. So in .NET 2, we introduced the event-based asynchronous model. In this model, I start by registering some code that I want to run when my asynchronous operation completed. This is exactly like it says, it's an event model, so I register an event to run. I then go ahead and kick off the asynchronous operation, and when it's completed, the code that I registered with the event handler will be run. This is good because I no longer have to continually poll the result, but on the downside, I have absolutely no transparency into what is actually happening as the asynchronous code executes. The only thing I get is an event at the end that says it either completed successfully or errored out. This brings us to .NET 4, when we introduced the task parallel library. In this programming model, we call an asynchronous method, which gives us back a task. The task is strongly typed using generics. So on the task, there's a result property, which gives me the strongly typed result. I then need to watch the task until it's completed, and then I can get the result from the task. This sounds a little bit like .NET 1.1, but the task class is much more featured. So, for example, there's a continue with method, which allows me to register some code to be run when the task completes. So that gives me the benefits of the event-based model that we saw from .NET 2. So in our most recent release of .NET 4.5, we introduced some new keywords, async and await. What we wanted to achieve with these was to make asynchronous programming much simpler. So we wanted your code to be structured the same way it would be written if you're writing synchronous, but have the compiler go ahead and create asynchronous code for you. This is what we're going to be digging into during our talk today, the async and await keywords and how they can be used in ASP.NET. So now we know where async has come from, let's look at the different places that async might be useful for you to use in your applications. Before we do that, let's just clarify exactly what we mean by asynchronous programming. Asynchronous programming and parallel programming are two very related concepts, but they're actually not exactly the same thing. Parallelism is all about running multiple operations at the same time. So I might kick off two requests to two different web servers, and those execute at the same time, and they might start and finish at very different times. The counterpart to parallel is sequential, right? In sequential, I write my code, and one line of code is not going to execute until the line above it has completed. Asynchronous programming, in the context of async and await keywords, is all about not blocking the thread while the thread doesn't have any work to do. So using the example of the web request, I might send off a request to a remote server. While that request is being processed by the remote server, there's nothing for my application to do. So I could sit there and block the thread, or I could free up the thread using asynchronous programming and register some code that's going to run when the remote request comes back. So the flip side of asynchronous is synchronous, and that's the scenario I mentioned, where the thread is actually blocked even though there's no work to do. So the two main scenarios we're going to look at today. The first one is going to be processing I/O operations asynchronously. So this is a scenario that I just mentioned where I send off a request to a remote server. The remote server does some work, and the thread on my client application or my ASP.NET application is free to go ahead and do other work while I wait for this request to come back. In addition to web server requests, we could do things like database access, because there's nothing for my managed code to do while I'm waiting for the database engine to return results for me. Or a file read, where I'm waiting for the operating system to read a file from disk. Once we've covered that, we're going to look at how asynchronous plays into parallelism and the appropriate times to use that, as well as some caveats for when not to use it. There is a third scenario that I want to mention, but we're not going to spend any time on it today, and that is the long-running event-driven. I've put up streaming there as an example. Streaming is a good example because there's some data, so I read it and process it, and then my thread can go to sleep because there's nothing to do, or I can give the thread back to the thread pool. At some point in the future, there's going to be some more data coming in, so I need to wake up and process it. These are very complicated scenarios, and we actually build some frameworks to help you with these. One great example of that is SignalR. So if you're interested in these type of scenarios, I'd highly recommend the SignalR talk tomorrow afternoon. So before we dig into code, let's look at I/O operations and some useful analogies to help us understand what is happening in the server. A good analogy to help us think about traditional synchronous web requests is to think of going to the post office. When I go to the post office, there's a set of employees assigned to work at the counter. As customers come in, they walk up to each of those employees, and the employee is busy during their interaction with the customer. For a lot of requests, this is fine because the customer has a short request, it's processed quickly by the employee, and the employee is then free to go ahead and process other people as they come in. Where this falls down is when some of our customers become slow. Now, this could be because they're having a long dialogue with the employee, and they actually need to be talking to the employee. But at the post office, chances are they're sitting there doing something that doesn't require the employee's attention. They might be writing a check, they could be looking at a message on their phone, putting their keys back in their purse or something like that. This is fine provided that there are employees free to handle incoming customers. Where this gets to be a problem is when I have all the employees taken up with people who are doing things that don't require the employee's attention. At this point, the line backs up and everybody gets very frustrated waiting their turn in line. In the world of web requests, think of this as a web page that needs to make a call off to a remote server and then just sits there holding onto the thread while it waits for that call to come back. There's nothing for that thread to do, so it could be freed up to process other applications. Here's an example of some synchronous code. I've taken this from an async white paper, which I've included a link to at the end. And we're going to use this code as a little example to look at asynchronous changes before we dig into actually writing some code in Visual Studio. This code is very simple. It takes in a list of URLs, loops through them, sends off a web request for the URL, and then sums up the amount of data that comes back from each page. Not particularly useful, but good for demonstrating purposes. So if going to the post office is like running synchronous code, a good analogy for asynchronous code is going to a restaurant or a coffee shop. When I go there, there's a set of employees that are allocated to process all the customers on the floor. As customers show up, the employees are free to go and talk to the customers and process their requests. For some customers, this is going to be really quick. They may just want a menu, they may just want to pick up a takeout order. In that case, the interaction is dealt with once, and then the employee goes on their way, and the customer goes on their way, and the employee is free to go back and serve other customers. Some customers are going to take up more time. So these customers might be looking over the menu, or they may be eating the food that they ordered. The employee doesn't need to stand there and wait for the customers to finish. In fact, that would be very annoying in a restaurant. Instead, they can go back to the floor and serve other customers as they come in. Some of those customers may be served immediately. Others are going to need several interactions to complete their request. As customers get to a point where they need interaction with the employee again, the employee is free to go back and process them. Some of them will then be done. Others will need a little more time, and the employee is freed up again to go and process other requests as they come in. The analogy here being, if we're able to free up some threads on our web server, instead of waiting for tasks to complete, those threads are free to process other requests. So here's our synchronous code, and I've highlighted the API call that's a really great candidate for asynchronous programming. The download data URL basically, or the download data for the URL basically pauses while it waits for the data to come back from the server. This next slide I'm going to show you will hopefully scare you a bit. You don't need to understand it. Prior to .NET 4.5, this is an example taken from the async white paper I mentioned about the type of code you would need to write to have very robust and scalable asynchronous code, dealing with things like error conditions and freeing up resources when you completed. The code actually gets more complicated than this in the white paper. I just wanted to pick some interim stage that would fit on the slide, but illustrate that it was really complicated to do. So going back to our synchronous code, let's see what changes we need to use async and await. As you can see, the code is structured very similarly, with a few small changes that I'll walk you through. Once we've done this, we're going to go and take these concepts and apply them to an application. So the first change is to mark our method as async. This is basically telling the compiler that at some point my method is going to return, but it hasn't actually finished doing its work yet. The thread is then free to be used for something else until my method signifies that it needs to do some more processing. Because my method is going to return before it's completed, I can't actually just return the result. What I'm going to do is return a task of the result, in this case the task of int. The caller of this method can then poll the result, and when it's ready, process the actual result from inside it. I'm tacking the word async onto the end, which is just a convention. You don't have to do this. But if you look through the .NET framework, you'll see all the asynchronous APIs have the word async on the end. The two changes within my method, I'm now calling the async version of download data. I just call out here that it's called task async on the end. You may have been expecting async, but there was actually already a download data async in .NET 2.0. So for APIs that already have a download data async, the general convention is to call this one task async. Now remember, because it's an async method, instead of returning the actual data, it's going to return a task of the data, and I need to wait for that task to complete. Now because I actually want to do that in my application, I'm going to use the await keyword, which is telling the compiler, at this point, my method can return, you're free to use the thread for something else, but at some later point, when this web request comes back, you're going to have to reload up my method, finish executing it, and then process the result into the task. So let's go ahead and see this in action. I've got Visual Studio open here. I've got an existing web forms application. We're going to start with web forms, and then we're going to go ahead and look at some other ASP.NET technologies as well. This web forms application is completely synchronous at the moment. So we're going to go and look at a few areas of it and change them over to be async code and see how that affects our application. To start with, we're going to focus on the dashboard.aspx page. There's really two parts to this page. At the top, I have a quote of the day. This is coming from an internal service that we're going to look at a bit later. The other data-driven part on this form is of what's happening in ASP.NET. This data is coming from the RSS feed on the ASP.NET Codeplex project. It's actually, for this demo, coming from a copy of that feed on my box, just because we're at a conference and the network's a little unreliable. The other thing I'm writing out to the page is the total processing time. This is the time it took for my code to execute to calculate all of these results and content. Let's look at the form in Visual Studio. The form itself is a very typical web forms application, or web forms page, just some simple markup there. The code for it, we go ahead and start a timer. We then, in the second code block, go and poll off to my internal service. This is actually a web API service. Get back some JSON, deserialize it into strongly typed objects, and then we bind it to a label that I have on the screen. We then do the same thing calling the RSS feed. This time it gives back XML. So I have a simple little helper method to help me deserialize the XML. It's just linked to XML. And then we bind that to a data list that I have on the form. We stop the timer and write out the total processing time to the screen. I'm just going to refresh this, and you'll see the first request might take a while. But after that, at the moment we're running at about 220, 230 milliseconds to process the request. The other thing I have in this solution is a set of load tests. So I'm going to go ahead and kick one off so that we can compare what happens as we make this application asynchronous. This web test has a 10-second warm-up on it. This is to make sure our application's up and running. It's then going to throw a constant load of 500 users at our web page for a period of 20 seconds. 20 seconds isn't really long enough to run a load test, but it should give us some results that we can use to see the changes. Those 500 users are doing one of two different things. They're either hitting our dashboard page, which has a bit of processing to do to pull the data from the two different services, or they're hitting the home page, just default.aspx, which has zero implementation in it, so it's effectively static content. The section that we're interested in is this test results section, or page results, sorry. I'll zoom in so you can see it. We can see here that our dashboard page has an average page time of 4.7 and the home page of 4.6, and we got through 450 to 500 requests in the 20 seconds that our test ran. You can see that I'm really starting to cripple my local web server, because before I was getting response times of about 200 milliseconds, and now it's got up to 4.5 seconds. So there's quite a load on it. All right, let's go back to our code and make it async. Remember, any method that calls async code needs to be marked with the async keyword. So I could go ahead and make my page load async. This will work in some very simple scenarios with web forms. However, it will fall over if you try and do anything particularly complicated. So what I would recommend instead of doing that is to use the register async task method. In this, we specify a code block using a Lambda expression that basically says, here is a section of code that I want you to run asynchronously. Interestingly, if I had made the page load method async, then the ASP.NET pipeline, or the web forms pipeline, or page lifecycle, would have halted at that point and waited for all my asynchronous operations to complete. By doing this, I'm giving ASP.NET a handle to a task that I want it to run at some later point. ASP.NET will then pick the best time to run the task, and it's going to be just before pre-render complete. So we could swap this to be the download string task async method, but I'm actually going to swap over and use HTTP client. This is the new and cool class, the new way of doing things. It actually only supports the asynchronous pattern as well, so I can't do synchronous requests with this. I'm going to call the getString async method. And remember, this returns a task, but at this point, I want my application, or this bit of code, to give back the thread and just wait for the result to come back. So to do that, I use the await keyword. I'm then going to make exactly the same set of changes to the second web request as well. All right, let's go ahead and load our application. And I'm going to get an error. The reason for this is because we run in a different page lifecycle, and there are some nuances that you need to be aware of when you run async code, we want you to very explicitly actually opt in to the async page lifecycle. So to do that, I'm going to go back to my ASPX page. And there's a page attribute async, which is a Boolean, so I'm going to set it to true. And this is telling web forms that I'm happy to opt into the asynchronous page lifecycle. We'll refresh again. The first request will take a bit longer. But we see after that we're still executing at roughly the same request time, maybe even a fraction longer because we're doing a bit of thread switching with the await keywords. So what was the point? If it didn't make the request any quicker, well, the point is, for one user, it doesn't actually make any difference. But if I throw a load at the server, I'd expect to see better results because I'm no longer locking the threads while my tasks execute. I'll go run the load test again. The tool that I'm using here is the load test functionality that comes in Visual Studio, but it's actually only there if you're using Visual Studio Ultimate. So if you're using a lower SKU, then there are some free tools you can use. One that I would recommend is WCAT, which is a command line tool. WCAT stands for the Web something analysis tool. It's gone from the top of my head, but anyway, WCAT, that's a tool you want to go and download. So let's look at our page results in here. So for the dashboard page, remember before we saw a request time of 2.5-ish seconds. So we're seeing a similar request time here. But for the home page, we're seeing a request time, instead of 2-point-something seconds, it's executing in 0.23 seconds. That's way quicker. And if we look at the throughput, remember we were getting sub 1,000 before. Now if we look at these, you can see we're getting way, way, way higher request count through. So why is this? Well, it's because while my dashboard page is executing, it's freeing up threads. And particularly for the homepage requests, that means there's a thread that's there available to pick up the request and execute it very quickly. A view that highlights this really nicely, if I load up this one, the blue on this screen represents requests to the dashboard page. As you can see, they're fairly long and they're blocking the thread for the whole time. The same thing is happening for the home page. Because there's no threads that are free to process a request, it's blocked for a large amount of time and then it executes quickly at the end. If we look at the same view of our second load test, we'll see the blue requests for the dashboard page take about the same amount of time, but we see tiny little segments of time taken to process the home page in between each of those requests as they're paused, waiting for data to come back from the client. Okay, so what do we want to take away from this? Well, await is a really great way to free up threads on our server so that we have more threads free to process incoming requests. Interestingly, we saw that making it async didn't really affect the client. The only noticeable difference for the client was that requests ran a lot quicker when there was a heavy load on the server. We need to opt into the asynchronous page lifecycle by setting async equals true for the page. I'm recommending that you always use register async task. This lets ASP.NET take care of the appropriate time to run your code. My last point here is that ASP.NET takes care of thread affinity. What does that mean? Well, there's some intrinsics, we call them, within ASP.NET, things like HTTP context.current, or the response, or the request. These are things that in the past were not safe to talk to or to use on threads, on different threads, other than the main request thread. As we introduce the await keyword, we're probably going to swap physical threads. There's one thread that's going to execute the first part down to the await. At that point, the thread goes back on the thread pool, and at some point later, my code is going to get picked up again to be executed, highly likely on a different thread. In the past, this wouldn't have been safe. But now ASP.NET is taking care of making sure that the context and the request and the response, and I was even able to access the label and the data list on my web form, and that was safe to do from a potentially separate physical thread. So provided you're using the async and await keywords, ASP.NET is going to take care of a lot of this stuff for you, and you're able to write simpler, much easier to read, safer code. So we saw web forms. Now let's go and take a look at Web API and MVC. we saw that our web form page was hitting a web API controller, and I've actually got that in a separate project here. If I go and look at the service project, in the controllers folder, I'll see a quote of the day controller. This is an extremely simple controller. All it's doing is using Entity Framework to go ahead and read a quote from the database and return it to the caller of the web API. The only thing I've really changed in this project, if I go and look at my references, is I've upgraded the version of Entity Framework that I'm targeting. You can see here that I'm targeting EF6 Beta 1. Why did I do that? Because EF6 is going to introduce support for asynchronous query and save. So we want to make use of that in our web API. Web API is actually extremely simple to do asynchronous programming with. There's no real page lifecycle or anything going on here, so I'm free just to go and mark the action as async. Because my action is going to return before the result's actually available, I need to update the return type to be a task of quote. Just resolve system.threading.tasks namespace. And at this point, I'm free to write asynchronous code. I'll just zoom in here for you. You'll see that looking at the IntelliSense for my entity framework query, in addition to find, or first is the one we're using here, we have a first async. So the entity framework has introduced asynchronous versions of all of the methods that would result in the query actually being sent to the database. So for example, operators like where, they don't have an asynchronous version because where doesn't cause the results to actually be pulled from the database. It's only when I ask for them with toList or first or count that I'm actually running the query. So we'll go and swap to first async, and we can now await on this. And I'll build my application. And remember, our dashboard page is going to hit the web API. The first web request will take a bit longer just because the service has been recompiled and everything. But after that, I see I'm still experiencing exactly the same request time, which is expected, right? Because we're not doing anything for performance here. All we're doing is now freeing up threads on the web API service as well. One really important thing to note here is I didn't make any changes to my web forms code. So the fact that I made the web API action async has zero impact on the user calling it. Web API takes care of hiding the fact that it's async and then appropriately calling it and waiting for the task to complete and then giving it back to the user or the caller. So our takeaways from this little bit, async is dead simple in web API. And MVC uses exactly the same patterns. If you have an action on an MVC controller, you're free to just go and mark the method as async and change the return type to be a task of your result. Like I said, async is completely transparent to anyone who calls the web API service, so they don't need to know that you're going to be freeing up threads while it executes. And not directly related to MVC and Web API, but Entity Framework 6 is introducing asynchronous database calls. This includes query and save. So far for our I/O operations, we've looked at successful requests, where things actually go through. But there's another category of requests, which is where the request, something goes wrong, and the request either doesn't complete or doesn't need to complete. What it would be good to do then, if I detect an error condition, is rather than letting my asynchronous code continue executing through to the end, it would be great if I could just terminate the request or terminate the asynchronous code and give that thread back onto the thread pool to process other requests. Async has a built-in mechanism to deal with this. They're called cancellation tokens. This allows a caller to pass in a token, and at any point the caller can mark the token as cancelled, at which point the asynchronous code should pick that up and terminate itself. This includes in-flight asynchronous tasks. So if I'm running a database query, I should be able to just terminate the query at that point. Fortunately, ASP.NET makes this really easy. We have 3 built-in tokens for us to use. Request timeout is an obvious one. If our request times out, then we have a cancellation token that we can use to kill any pending async work. Client disconnected might be I close the web browser, and therefore I don't need the results of the request. And there's also a new asynchronous timeout. This is an individual timeout for asynchronous operations. So I can say that no async operation that runs in my page should take more than 300 milliseconds to complete. So switching back over to our application, I'm going to load back up the code for our dashboard page. And I'm going to set a couple of breakpoints. The scenario I'm going to look at is the one where the user closes their web browser before the request completes. So I'm going to let the code run and hit this first breakpoint. I'm then going to let the code continue executing, but before it continues, before this asynchronous task completes, I'm going to go ahead and close the web browser, and we'll see that the second breakpoint, well, it shouldn't get hit. We'll look at the fact that it does first, and then how we can stop that from happening. Now, I'm probably not quick enough to actually close the web browser while that quick little web request is happening, so I'm going to introduce a bit of a delay in here. So we'll put a 3-second delay on here. Fortunately, there's an asynchronous way to delay, so we're not actually going to lock the thread for 3 seconds. We're going to do it asynchronously. And I'm going to run with the debugger attached this time. So let's put Visual Studio in one half of the screen, IE in the other half, and this is just a normal web request, so I'll let it go through. My first breakpoint gets hit, I press F5, there'll be a delay of about 3 seconds, probably a bit longer on this first request. Then it will come back, our second breakpoint is hit, I press F5 and the request completes. I'm going to start up a second tab and hit the same website. So we'll see our first breakpoint gets hit. What I'm going to do is press F5. You'll see that happen when the line that's highlighted goes back to being red. That means I've pressed F5 and Visual Studio is continuing on. At that point, I'm going to go ahead and close this second tab. So pressing F5, closing the tab. But we see that our second breakpoint still gets hit. Our code is still running on the server. So I mentioned that ASP.NET has some built-in tokens that we can use. If I look at the response object, I'll see that there's a client disconnected token. So this is a cancellation token that I can then go ahead and pass into my asynchronous APIs. So I'm going to pass it into all three of them. So now that we've got the client disconnected token wired up, let's go ahead and run with the debugger again. So our first request is going to hit my first breakpoint. I'm going to let it complete. So there'll be a 3-second pause, second breakpoint, request completes. Let's fire it up in another tab. First breakpoint is hit. Press F5, close the tab. And our second breakpoint isn't going to get hit. So as soon as I close the tab, the client disconnected token is fired and my asynchronous calls cease. Depending on how fast I was, if I was Jedi fast, it might have happened during this getString async. It's probably more likely that it happened during the task.delay that I had running. So what about Web API and MVC? Well, actually, before we do that, I mentioned that there's 3 cancellation tokens, but I'm just using 1. And the APIs that I'm using only let me pass in a single cancellation token. So what we'd really like to be able to do is to wire all 3 cancellation tokens up into a single one. So to do this, I use cancellation token source, create linked token source. This is going to give me a kind of composite token built up of several individual tokens. So we'll pull in the response token. That's the client disconnected one. The timeout comes off the request object, so the timed out token. And I mentioned one other token as well, which was the asynchronous timeout token. To get that one, I'm going to add a parameter to my Lambda expression. If I mouse over and zoom in for you, you'll see that it's typed as a cancellation token. So that gives me the third token that I want. And I then go ahead and update my token to come from the source. So if I go source.token, that will give me this composite cancellation token. So that's how I wire all the three up in web forms. Going to our Web API controller, it's actually simple here. All I need to do is pass in or add a cancellation token parameter to my action, and then I'm free to pass that one through to any asynchronous operations I run. Web API, and the same is true in MVC, is going to take care of putting the correct object into that parameter for my method. And the fact that I've changed the signature of my Web API action has zero impact on other clients that are calling this. Again, Web API is hiding all of the asynchronity of my action, and so callers just call it, and Web API will set up the correct cancellation token and pass it in. Now I need to confess, I actually cheated in this demo. If I go back to my dashboard code, you see I'm calling an overload of getString async that takes a cancellation token. If you try and do this at home, you won't be able to because it doesn't exist. I've actually defined it as an extension method in this project. So here I'm mimicking what getString async does internally. getString async calls getAsync, which does accept a cancellation token, so I'm able to pass it into there. But it then calls readString async, or readAsString async. This doesn't accept a cancellation token. So I just created this simple little extension method to make my code easier to write. So takeaways. Cancellation tokens are a good way to further reduce our thread usage because we're giving up threads that would have been used in executing requests that no longer need to complete. ASP.NET has 3 built-in tokens, which you should wire up. These will take care of the common error scenarios. And to wire them all together, if you have multiples, then you use the cancellation token source. So we've looked at all the different ways that you can use async to free up threads while you're doing I/O operations. But what about things that would actually have an impact on the way the page loads for the user? Well, let's take a look at parallelism. If synchronous web requests are like going to the post office, and asynchronous web requests are like eating at a restaurant, then parallelism is all about throwing as many resources as we have, or a set number of resources, to complete a job much quicker than one thing could have done it on its own. There are 2 types of parallelism. The first one that we're going to look at today, or this is the one we're going to look at, is running multiple asynchronous operations. So this could be 2 individual requests to remote web servers. They're asynchronous, they don't use threads, so I can just kick them off and they can run in parallel. No additional threads are used. The flip side of that is synchronous operations. This might be things like image processing or indexing, which actually do use a thread. For things like this, I'd be using task.run to spin up a new thread to execute work. In this case, each operation actually uses a thread, and so we need to think about the resources that we're using on the server. Now, you may think this is okay, because surely it's another thread pool that gets used for these tasks that I kick off. But it's actually not. It's the same thread pool that gets used to process incoming requests. So if you spin off work on another thread, you're using up a thread that could have been used to process somebody else's request. So our dashboard page is actually a really good candidate for parallelism because I kick off 2 asynchronous tasks, at the moment one after the other, but I could kick them off at the same time. So I'm going to start by moving the 2 lines to a little bit further up, and then I'm going to go ahead and take out the await keyword because we don't want to wait for one task to complete before we kick off the next one. Now the code below where my cursor's at, that does need the tasks to have completed to be able to run. So what I could do here is write await, quote JSON, and then I could also await on the RSXML. This would work, but a way that is slightly more efficient, and I think much easier to read, would be to await on task.whenAll. Like I said, slightly better performance. Now, because I took out the await keyword, the data types of my two variables have changed. They're no longer string, but task of string. And you can see here I've got some compile errors. Because I've waited on both of them to complete, I can be confident that they've both got a result by this point, so I can just go ahead and pull out the result. Let's load it up in IE and see what's going on. Okay, so our first request is going to take a little bit longer to run. But if I press F5 again and refresh, actually I've still got the thread delay in there from my last demo, so let's take that out. So this time around, our first request should take a little bit longer. So remember before our requests were taking around about 220 or 230 milliseconds. We see now that they've dropped all the way down to 110 to 120. So what can we take away from this? Well, parallelism is a great way for us to reduce the request time. But we need to be very careful if we're doing synchronous parallelism, because spinning up multiple threads is going to starve the thread pool that would be processing incoming requests. Now, I said before that asynchronous requests are fine. They're not going to use any extra threads. There will be a little bit of overhead, but pretty negligible. That's definitely true for the application that is making the calls. But if I'm spinning up, say, 10, 20, 30 asynchronous requests on my one request and sending that off to a server that's inside my organization that I own and pay for the resources for, then I could be flooding that server, and I'm going to end up introducing a bottleneck there. So synchronous, it definitely costs more. Asynchronous, you've got to think about what you're sending the requests off to. If it's outside your organization, probably go for it. You may bring their server down. If it's inside, you really need to think about it. Oh, I didn't say that, sorry. Go back. Especially not if it's our ASP.NET Coplex site. Don't do that. So we've looked at web forms, we've looked at web API, and MVC follows exactly the same patterns as web API. Now let's think about what we've learnt, let's take what we've learnt and apply it to somewhere else inside ASP.NET. We're going to dig a little bit further down the pipeline now and go and look at an HTTP handler. So in a nutshell, an HTTP handler is a piece of code that knows how to process a request for a particular file type. So built into ASP.NET, there's a page handler or an HTTP handler that knows how to process requests for ASPX pages. It knows how to load up an ASPX page, run all the appropriate code, and somehow pull all that together into a response that can be sent back to the client and interpreted by their web browser. There's also another handler that knows how to process web services and things like that. Switching back to my application, I'm going to load up the web.config for the web forms application that we have. And I'm going to call out one section where I'm actually registering a custom handler. This one here, you'll see I'm registering it for anything that ends in .info. And I'm telling it to go and load up the mybiz.info handler that lives inside the mybiz assembly. So that's a class that I've written to process these .info requests. So I'll load up the code for that. For HTTP handlers, there's basically one method that is of interest, which is process request. This takes in the HTTP context, and from there I can write to the response to put together all the information that should be sent back to the client. I start by looking at the actual request path that was sent in. For this handler, I expect it to be in the format of a 5-digit zip code followed by .info. So I have a helper method there that will validate that that's the case, and if it's appropriately formatted, it will return me the zip code. Once that is done, I go and write out some basic HTML to get the page started, and I then have these 3 calls off to helper methods, which start to put together some HTML content to send back to the user. This is information about the zip code they sent in. So I have some interesting facts about the location, some general information about it, as well as the current weather at the location. When all that is done, I go ahead and stop the timer and write out the total processing time, and then end the HTML and send it all back to the client. I'll just look at one example of the helper methods. They're all pretty much the same. We see here create info section. It uses code that we saw before, web client, to go and hit a web API, get back the results in JSON, deserialize them, and then put together some HTML based on the results. Let's look at a quick example. So I'm going to enter 98052.info. 98052 being the zip code for Redmond, where I live. And we can see some interesting facts, general information, weather comes back. The processing time is horrible on this page. At the moment, it's 2.5-ish seconds. We got 2.7 on that request, 2.6 on this one, so really slow. And that's because the services that I'm querying are very slow. Or I should say I made them very slow to help demonstrate my point. This would be a really great candidate for async and parallelism, right? We could take the concepts we've learned and fire off all these requests at once. But I can't write async code inside something that implements iHTTP handler. So I could go ahead and try and implement iHTTP async handler. This thing's quite complicated to implement. It has a begin process request, end process request, and it also has to implement iHTTP handler, which has these methods on it. So it's not that many methods, but it would be quite complicated to wire this thing up correctly. Fortunately, we do all that work for you. There's an HTTP task async handler. So I'm just going to change the method signature of my process request method. So we can see that this is an async method. And this is actually the only thing that I need to do to implement this base class. It's the one method on there. And now I'm free to write asynchronous code in here. So we saw before that I could go ahead and make this call to create fact section asynchronous, and then I could await on it. But that's still going to have a very horrible page load time. What it would be better to do is kick off all the tasks at once. So I'm going to kick them all off, and I'm actually going to store them in a list. And we'll see how this pans out a bit later. Now, you guys know how to write asynchronous methods by now. So I've already gone and created asynchronous versions of the methods. So the only difference between these and the synchronous versions is they're marked as async with the task return type. I've postfixed them with async, just to call out that they're async. And then, as we saw before, the query off to the client is asynchronous. So we can call these passing in the zip code. So we want to get the facts, we want to get the information, and finally we want to get the weather. Unless we're in Redmond and we probably don't want to know what the weather is. All right, so we've got all of those done. Now, we could wait for them all to return, right? But some of them are going to return at different times, so better than waiting for them all to return like we did in the last demo, let's process each request as it completes. Some will take longer, some will be quicker. So as each one completes, I'm going to take it out of the list of tasks. So we're going to do a while loop, and we'll keep iterating while there are any tasks left in the list. At this point, we need to wait for something to happen. So I'm going to await, and instead of calling when all, I'm going to call when any. So this will fire when any of the tasks complete. When any actually returns something to me, it gives me the task that completed. So I'm going to assign that to a variable. The first thing we want to do is remove it from the list of tasks. So we'll go ahead and remove it. Now that we're confident that this particular task is completed, we're free to use the results. So we've got the HTTP context, which gives us access to the response, which we can then write to. Remember, this is all strongly typed, so my result is already typed as a string. Now, I could stop at this point, but what it would be great is to actually push this information out to the user so they can see it without having to wait for everything to return. So I'm going to do a flush here. So that'll push the results out to the user. Now, one thing we haven't dealt with yet is what if something goes wrong while the task is actually executing? So in this case, I might want to just ignore something. If something happens and there's an error condition while I'm getting the weather, well, no big problem. I just won't display the weather on this request. So I could check the is faulted on here. And we want to do the opposite of that. So if the task comes back, provided it's not faulted, we'll go ahead and push the result out to the user. So we'll go ahead and press F5. Looks like we forgot to do something. Oh, let's take that out. I'm doing something wrong there, but all right, so we see now that data is incrementally pushed back to the client, and we're seeing a much better response time. It's still pretty horrible, but the request time is only as long as the longest running task, about 1.6 seconds at this point. This code is pretty good, but there's actually one thing here which is running synchronously that I could swap to be async, and that's my response.flush. Unfortunately, though, if I look at the methods to do with flush on the response, there's no flush async. In fact, I'm stuck with the .NET 1.1 concepts of begin flush and end flush. Now, I really don't want to write code to deal with those, but fortunately, the guys that implemented the task class were thinking of this. So I can say task.factory.from async. And this method is cool because it lets me pass in pairs of begin and end methods. So I want to begin flush. Make sure we get end flush instead of end. So this has given me a task now, so task parallel library style call, to something that was .NET 1.1 style. And of course this is awaitable. Okay, so now we have a good web form, it's kicking, a good handler, it's kicking everything off in parallel, using as little time as possible, and it's freeing up threads whenever it doesn't need them. So in the remaining bit of time we have, I want to look over some tips, some tricks, and some things that you should very, very passionately avoid as you're writing asynchronous applications. Avoid work on background threads. If I'm writing a console application or a WinForms application, then background threads are a really good idea, because if I do work on the main thread, I'm going to be locking up the UI. But in a web request, there is no UI to lock up. So you might be tempted to think, well, I can kick off a background thread to do some image processing or something, and surely this will free up the current thread to be available to process other requests. Remember, that doesn't hold because there's only one thread pool. So that extra thread that I'm spinning up is going to take away from other requests. This just adds cost too. If I'm thinking that I'm going to put it on the background thread and then free up the current thread, well, I have freed up the current thread, but I've also taken up another thread, so I've just incurred the cost of doing a thread swap for no reason. Now, you may come across cases where you need to execute both synchronous and asynchronous code within a method block. Some conditional paths are going to result in asynchronous code being run, and other paths, there's going to be no asynchronous code to run. An example would be a method that detects some input scenario and short circuits to a predefined result. So if I wanted to return, say, 5 from my method, but my method is marked as async and returns a task event, then I may be tempted to do task.startNew and write some code that will return 5. If I do this, I'm going to spin up a thread just to process that little bit of code. A much better option is to use task.fromResult, which will give me something that looks like it executed asynchronously, but is actually just a static value that I can put in. If you need to return something that isn't success, say you want to return faulted or timed out or something like that, then task completion source is the class that you want to use. We talked about ASP.NET intrinsics, so this is things like the HTTP context.current or writing to request response or trying to access controls on a web form, things like that. You can't do this from a worker thread safely. So how would I do this? Well, the simple answer is just use async and await. ASP.NET will take care of everything if you do that. The one caveat is that you must start using await and async from the thread that the request is actually on. So I can't spin up a background thread and then start using await and async and expect everything to be wired up. I need to actually do it from my web form. There may be scenarios where you actually legitimately need to spin up a background thread and you want to be able to access these things. If you have this scenario, then go ahead and take a look at synchronization context.post. ASP.NET, well, it's actually a generic mechanism built for asynchronous, but ASP.NET has some classes that will help you do things in a thread-safe manner. This is a fun one. Task.wait sounds very harmless. It sounds like you're just going to stand there and wait for the task to complete. Well, the problem is it actually blocks the thread while it's waiting for the task to complete. The same is true if you try and access the result of an asynchronous operation that hasn't completed. The current thread is going to be blocked. And I mean proper blocked, not like freed up and it will come back to your code later. We'll actually hold on to the thread until your asynchronous task completes, and then it will get the result and your code will continue. Now, this may sound like it's just going to cause bad performance, which it will, but in ASP.NET it's actually worse than that. Because ASP.NET is doing all this work to keep the intrinsics available, regardless of which physical thread you come back on, it's very easy to deadlock ASP.NET using wait. So the solution, as we've seen today, is to use await, or if you want to wait on multiple tasks, use tasks.whenAll. I actually want to show you how easy it is to deadlock ASP.NET doing this. So in my default page, I've gone ahead and marked the page as async, and I've got a simple little async method here which basically just sets up a delay for 100 milliseconds. I'm going to go ahead and register an async task. And in here I'm going to call my doStuff method and then call wait. Looks harmless. You'll notice the compiler is actually very smart. Just going to zoom in. You'll see that async has a green squiggle under it. So it's still going to compile and run, but it's warning me the code you've written here actually isn't asynchronous because I haven't used the await keyword anywhere. But because it compiles, let's just go ahead and run this. And we'll wait, supposedly 100 milliseconds. But not, because we've actually locked up ASP.NET. The problem is, I'm executing on one thread, and it has the ASP.NET intrinsics are doing a bunch of locking to make sure that everything is safe to access. So it's got a hold, there's a bunch of locks in place, and then I'm trying to spin up some work that is going to potentially come back on different threads. And so ASP.NET is trying to do a bunch of work, but I've got two threads and one of them's locked and it can't really transfer control to the other code. So at this point, ASP.NET is in basically a deadlock. So the correct way to do this is to await on our task. You'll see now the green squiggles will go away when I build. And if I run, we'll see a short 100 millisecond delay, and my page loads correctly. So I mentioned back when we were looking at .NET 4.0 and the task parallel library that task.continueWith was a way to, in an event style-ish manner, register some code to be run when my task completes. This is kind of redundant now that we have await. So continueWith is not aware of the synchronization context, which means all the work that we do in ASP.NET to make the intrinsics available to you isn't relevant. And it always puts you on a new thread too. It's going to launch up a new thread to run the code that you put in continueWith. So don't use it. Use await instead. It does exactly the same thing. Or I should say it achieves the same thing but does it very differently. We mentioned parallelism a couple of times too. So on a desktop application, parallelism is great. Say I need to process 100 images. Well, I can spin up 100 threads on a desktop and that's fine. It's not going to hurt anything. If I'm on a web server and I have one request coming in, I can spin up 100 threads too there. That's not going to cause any issues. But if I'm on a real web server that has some actual user load on it, and all of those requests that are coming in, hundreds, thousands, tens of thousands of requests, if they're all spinning up tens, hundreds, thousands of worker threads, then I'm going to very quickly starve the threads on my server. Interestingly, I'm going to start digging into memory. When I start talking about that number of threads, and at a minimum each thread uses a 1/4 megabyte of memory, I'm going to max out the memory on my server pretty quickly too. And remember, I said kicking off multiple asynchronous tasks is great. Just keep in mind where you're sending those tasks to. You're sending 1,000 tasks per request off to another server that you pay for the resources for. You're just kind of flooding that and transferring the load. Thread local storage is not an option when you're using async. Thread static and other equivalents and things like that, you can't use them. Your code before any awaits is going to execute on one physical thread. At that point, that thread goes back in the pool and can be used for something else. So any code that executes after your await, it's pretty likely it's going to execute on a different physical thread. The safe place to put stuff, because ASP.NET will take care of all the intrinsics for you, is to put it in HDB context.items. Now you probably think, well, that's good, so I'll remember that for my asynchronous code, and my synchronous code I'll still use thread static for. Don't. If you have any asynchronous code anywhere in the pipeline, it can swap physical threads on you. So even though your code is synchronous, don't assume that it's all going to execute on the same physical thread. This is one of the reasons that it's great that we kind of have an opt-in to the asynchronous page lifecycle. It means things like this don't just automatically bite you. Fire and forget methods. This is something where I kick off an asynchronous task, but I don't do anything to wait for the result to come back. So I don't do an await on it. I don't use the result anywhere. Because I'm running in a web server, as soon as the request finishes, if my method that I fired off and didn't listen to the result of is still executing, it's highly likely that that code is just going to get terminated because the request is finished, so the thread needs to be cleaned up and stuck back on the thread pool. Fortunately, there's ways to do this appropriately. So if you have very simple work to do, then you can go ahead and grab the web backgrounder package off NuGet. This is a package that uses some safe and appropriate ways to fire up worker methods or some worker code that needs to execute in the background. However, if you're doing something very complex, then you're probably going to want to go and write a proper worker process. So a worker role that's going to run, it's not a web request, it's running as a service or something on the machine, and it's doing the work that you want done in the background. Some examples of this would be image processing, where you want to loop through all your images and put watermarks on them, or perhaps you're doing some indexing. Web Backgrounder is super simple to use too, so don't feel like, wow, I'm going to need to write some really complicated code to do this. It takes care of it all for you. We actually got to see this one in action. If you don't need to, please don't try and implement HTTP async handler. It's pretty complicated to get right. You're much better off using the base class that we provide. Has a single method. It's actually easier to implement this base class than it is to implement HTTP handler. HTTP handler has basically the equivalent method and a property that you need to implement. Base class just has one method. Takes care of everything for you. So let's talk about some places you might want to head to next. The .NET team that deals with parallel programming, asynchronous, etc., has a blog. This is a really great place to go if you want to learn more about asynchronous programming within the .NET world. I mentioned the asynchronous white paper. So those code examples that I used when we were looking at restaurants and post offices, they come from the .NET white paper. That will give you a good in-depth look into why await and async are super useful, and the kind of knowledge that goes behind how to use them in complicated scenarios. If you just want to see these in actions, then head to the ASP.NET async tutorial. You'll find a lot of other great content too on the ASP.NET site. There's new stuff going up on there every week, basically. The other resource, if you've watched this demo and you thought, well, there's some stuff in there I'd like to see again, I'm going to be posting the source code from this on my blog. So my blog, you probably won't remember this, but it's romiller.com, romiller.com. But if you find the talk on Channel 9, I'll post it in the comments there, so you'll be able to find it from there. The other thing I really want to ask you to do as a speaker, and please do this for all your other sessions as well, is go and fill out an evaluation. It seems like it's just a boring thing that you're asked to do at every talk, but it actually really helps us in two ways. One, it helps us make sure that TechEd has the talks and the content that you like. So if you want to hear more of this kind of session, then let us know. If you don't, if there's other things you want to hear, fill out the feedback and let us know. It just helps us make the next TechEd even better, and the other conferences that we do. Number two, all of the speakers always want to get better at presenting content to you. So if there were things you didn't like about this talk or things that you think I could have done better, please fill out the evaluation and let us know. It really helps us bring content that really helps you do your job and be more successful writing applications. So with that, I'm going to wrap up. You get a couple of minutes early. I'll be down the front if you have any questions. You'll also find folks from the ASP.NET team in the Expo Hall in the Developer Center. So thank you very much for your time. Enjoy TechEd.